Vanakkam. Welcome to this course on classics in neuroscience. In this series of videos, we are looking at classic Nobel Prize winning works, and in this series, we are looking at classic Nobel Prize winning works of Edgar Adrian. In today's class, we will look at the St. Louis connection, that is the work of Gasser and Erlanger, and how Edgar Adrian's learning from Gasser and Erlanger helped him improve his equipment and instruments in a very big way, and how Alexander Forbes and his early contributions towards making the radio tube amplifier was instrumental in improving the recordings from the neurons or from the nerve tissue. So, we will start with a brief biography of Alexander Forbes. Alexander Forbes was from a prominent Boston family, so he was a well-known person in Boston. His mother was the daughter of the famous Ralph Waldo Emerson, and his father was a Civil War hero and the president of the Bell Telephone Company, so quite very well known at this time. So, Alexander Forbes attended Harvard, where he was very popular, and he did very well in football, and he developed an interest in physiology, and he received his master's degree in 1905 and his MD in 1910. So, he received his medical degree by 1910. He continued to stay at Harvard and as an instructor lecturer in the physiology department. It's a very famous and well-known physiology department. So, Harvard physiology is considered the temple of American physiology under Walter Cannon. So, Alexander Forbes studied under or worked under Walter Cannon at that time, and inspired by Charles Sherrington, Forbes took study leave from Harvard and went to England to study reflex physiology, and he visited Cambridge and collaborated with Keith Lucas and Edgar Adrian in the early 1910s. This collaboration led to new experiments. Essentially, he was supposed to travel in the Titanic, but his meeting with Keith Lucas and Edgar Adrian essentially made him to postpone his return back to the United States. So, he did not take the ship back to US in the Titanic. He did not take the Titanic back to the US because he decided to continue his study leave for some more time so he can work with Edgar Adrian and Keith Lucas, and essentially escaped. Because he decided to work with these two scientists, he probably escaped death. Through this collaboration, Alexander Forbes improved the capillary electrometer and the string galvanometer that was already there in Cambridge, and he returned to the US with new insights and essentially improved his lab with the advanced equipment and the ideas that he got from Keith Lucas and Edgar Adrian. But this collaboration also led to an improvement in the equipment at Cambridge, because the Cambridge equipment that was there, the capillary electrometer and the string galvanometer, were improved by Alexander Forbes. So, Alexander Forbes joined the Navy in World War I, where he was focusing on developing radar and wireless devices, and he learned about vacuum tubes or audions that could essentially enhance or amplify radio signal. This was the good old days, remember, this was the 1910s. So, post World War I, Alexander Forbes used vacuum tubes to create a new amplifier for performing physiological research. In 1919, his amplifier, the amplifier that he designed, it was a thermionic amplifier, essentially amplified the neuronal action potential by about 50 times, which was a phenomenal amount of amplification for those days. For comparison, today's EEG today commercial EEG systems, amplification is about 10,000x, and today's EMG amplification is about 1000x. But in 1919, when Alexander Forbes built his radio tube amplifier, or the vacuum tube based amplifier, it could amplify the neuronal action potential by 50 times, which was huge for that day. Okay, something, it is useful to keep that historical perspective. After all, this is a course on classics. So Forbes published detailed descriptions of his equipment, his amplifier, and how it can be used in neurophysiological experiments, and many of his experiments were on frogs and cats, and they were used to confirm existing findings, but he was doing it with greater precision. So his measurements were better because of his improved amplification. So essentially his accomplishment was not scientific in that sense, because he essentially confirmed existing and well known findings, but technological. He essentially greatly improved or enhanced the ability to amplify or magnify the neuronal action potential. So his work allowed other scientists of the time, other neurophysiologists, to use similar equipment to investigate phenomena in neurophysiology with improved clarity, with much better clarity than earlier. So essentially this was a great boon to neurophysiologists like Edgar Adrian and Charles Sherrington. Meanwhile, Herbert Gasser and Joseph Erlanger were prominent figures in electrophysiology. Herbert Gasser was Erlanger's student in University of Wisconsin. They both later worked together at Washington University in St. Louis, Missouri. So Herbert Gasser began the work on improving the instruments and the projects that would bring them an extraordinary amount of fame. Recall that Gasser and Erlanger are among the Nobel laureates who won Nobel Prize for their work on development of these instruments that improved understanding of electrophysiology. So Herbert Gasser sought to increase the amplification of the neuronal action potential beyond what was performed by Alexander Forbes. What was done by Alexander Forbes? About 50. Right? So Herbert Gasser collaborated with H.S. Newcomer, it's a name, Newcomer, and other physicists at Western Electric Company, and he developed a multi-stage amplifier. That is, an input from a neuron is amplified, and that amplified output is again amplified, feeding the output through multiple stages of amplifiers for greater magnification. Of course, today we know that it is not that simple. There are things called input impedance, output impedance, impedance matching and other such things, but that is a topic of instrumentation, but not now. But still they must have done this too. It is not like Herbert Gasser and others did not know that this is very challenging. So they also perhaps addressed this, and they performed initial tests on dogs' phrenic nerve, and that showed extraordinary promise and improved action potentials. Meanwhile, Herbert Gasser learned about improved cathode ray tubes in the 1920s. The original cathode ray tube and what was later to become the oscilloscope was first developed by German scientist Carl Braun. In the late 1890s or close to 1900, 1897 or so, these cathode ray tubes can display small changes in deflections without any mechanical distortion. So earlier the method was to make this measurement using on a roll of paper using a drum that is rotating with a pen that is writing this. So, there were several challenges that Gasser encountered in his attempt to build a cathode ray oscilloscope, and it was Joseph Erlanger who used his influence to acquire equipment and the necessary instruments and the consumables that is required for improving that device and further experimentation. Gasser and Erlanger's work led to the situation where they were able to amplify neuronal impulses by 7,000 times. From 50x they have come to 7,000x. They also found that there are different types of nerve fibers that conducts action potentials at various velocities. So, there was a classification of nerve fibers based on nerve conduction velocities, and their studies showed that nerve cables essentially has many types of fibers that have different functions. And so, there is light touch, dull pain, sharp pain, temperature detection or nociceptors that are associated with specific nerve fibers, and then there are fibers that conduct at very high velocities. And through their knowledge of electrical engineering, they were able to predict that the thicker neurons were the ones that could conduct faster, because that is how things worked in electrical engineering. That must be perhaps true in the neuronal conduction also. As to why that is true is something that we only know now because of the presence of myelin sheaths, because of myelination. That is something that we now know, but remember this was the 1920s and 1930s. So, but their hypothesis was true. Their hypothesis that the thicker nerve fibers necessarily are faster and those that are thinner are necessarily slower was indeed true. Also, the diameter of the neuron itself matters, the diameter of the axons matter. So, there are two things that come into the picture. One is the amount of myelination, the other is the original diameter of the neuron itself. As the diameter increases, the conduction velocity increases. As the myelination increases, also the conduction velocity increases. The reasons are not the same. For reference, I request you to check my videos on neuroscience of human movement, in which I discuss things like membrane resistance, membrane capacitance, and how length constant and time constant play a role in this beyond the scope of this course, but do check my other videos. So, Gasser and Erlanger were awarded the Nobel Prize for their work in 1944, and their improvements in technology and discoveries to study peripheral neuronal physiology were truly groundbreaking, and their work essentially paved the way for future electrophysiology based research that Edgar Adrian was pursuing later. So, with this we come to the end of this video. In this video, we looked at the St. Louis connection and the contribution of Alexander Forbes and his early contributions that he made in terms of making a radio tube or vacuum tube based amplifier, and the pioneering work of Gasser and Erlanger, who improved the work of Alexander Forbes to introduce multi-stage amplifiers that could amplify up to 7,000 times, using which they found that there are neurons that conduct at multiple velocities, different velocities, and that the thicker neurons were faster and the thinner neurons were slower, and so on and so forth. With this, we come to the end of this video. Thank you for your attention.